Hi, my name is Audrey Barszcz, and I'll be walking you through my exploration and machine learning modeling of the drug consumption dataset. The dataset I'm using can be found at the UCI Machine Learning Repository. It is called the Drug Consumption Quantified Dataset. The data was collected via online survey, and responses from about 2,000 participants were recorded. The data in this survey includes demographic information and personality inventory scores for certain traits. Along with these variables that can be used as features in a machine learning model, data on consumption of various drugs were collected as well. The drugs range from caffeine and chocolate to heroin and amphetamine. For each drug, participants reported their use by selecting a level ranging from never used to used in the last day, giving us 7 discrete classification labels for each drug. My particular research question focused on predicting the use of cannabis. I was interested in seeing if, using the available demographic information and personality scores, we would be able to predict the level of cannabis use. To begin, I'll examine the distribution of features. Based on the distribution of features alone, we can see that a majority of the participants in this survey were younger, have some college experience, are either from the UK or the US, and are white. The personality scores seem to be roughly normally distributed. We can also examine the distribution of the potential targets. Looking at the class label distributions of each drug, I chose to predict cannabis use because I thought the features collected may be predictive of the level of cannabis use. As we can see, looking at the cannabis use distribution, the classes are somewhat imbalanced towards both extremes, never used and used in the last day. Class 4, used in the last month, has the lowest frequency. Before I began modeling any of the data, I examined the data for missing values and class imbalances. Luckily, there were no missing values to impute in this dataset. As for class imbalances, this might be a concern when modeling since the majority classes are 2 to 3 times larger than the minority classes in the dataset. In an effort to rectify this, I will try using SMOTE in my pipeline and see if it improves the performance of the model. To split the data, I used 15% of my overall data for testing and split the remaining 85% of the data between training and validation. Additionally, I made sure to stratify my train test splits on Y so each subset of the data would have the same relative distribution of classes in Y. To evaluate and compare between models, I used the scoring metrics of balanced accuracy and F1 weighted score. I chose these two metrics because they consider multiple classes. The balanced accuracy score calculates the average accuracy score across all classes, weighing all classes equally. This is a more nuanced way to look at the correct predictions in comparison to the accuracy score that tends to obscure misclassifications of minority classes. In addition to the balanced accuracy score, I evaluated and compared models using the F1 weighted score. I used it as my scoring metric in the randomized search cross-validator as well. I chose to focus more on the F1 weighted score because it takes into account both precision and recall, weights them equally, and factors in the relative class weights within the dataset. I ended up choosing a random forest classifier for my data. I chose this algorithm because it performed the best on training using cross-validation comparison between different models. The first addition I made to the pipeline to try and improve the model was to incorporate SMOTE. The model ended up performing better with the addition of SMOTE. From there, I tried different column transformers for each column. I found that this helped the model performance for both categorical and numeric columns. For the categorical columns, all columns other than gender used a form of target encoder. For the numeric columns, the distributions of their data were close to normal, so the standard scaler worked for a majority of them. To finish tuning my pipeline, I performed a randomized search for the best hyperparameters for the random forest classifier. I found that tuning the hyperparameters for the random forest classifier hurt the model performance slightly. My final model yielded an F1 score of 0.351 and a balanced accuracy score of 0.303. Since these scores are so low, I would not put this model into use, nor would I trust its predictions to be accurate. I would not be surprised if the low metric scores have to do with the overall difficulty of classifying the data. There are 7 labels the classifier is trying to predict, and the distances between labels aren't very far apart, which resulted in a lot of misclassifications. In an effort to try and visualize how the random forest model actually yields a prediction, I produced this graphic of a single simple decision tree classifier. A random forest is composed of many, in my case 100, decision trees. Each decision tree is trained on a subset of the data, and at each node chooses from a random subset of the features. From that subset of features, the tree chooses the feature that yields the purest subsequent node. In this way, each tree in the forest is somewhat independent of the others, not just 100 copies of the same tree. The aggregation of predictions of individual trees is the random forest prediction. Some additional ideas I had for this dataset were to instead try turning the problem into a binary classification problem, collapsing all classes other than never used into a used class, and classifying used versus never used. Hopefully, results on this problem would yield more stable predictions and thus better scores on metrics. A classifier that performs well on this problem may also be more useful in a business context. With more stable predictions, one could look into the feature importance of each predictor variable and again try predicting the data using the most important features. A final idea I had was to perform some feature engineering on the personality scores. For example, we might be able to categorize participants based on their personality inventory scores and assign them a single label rather than using their scores on individual traits to try and predict their cannabis use. Thank you for listening.